In the eyes of the federal government, physical death is a data event. It is a state change, a single record written into a master database that decides who is alive, who is deceased, and who is allowed to exist inside America's identity infrastructure. In 1936, the government introduced the Social Security number. It was designed purely as an earnings tracker for retirement benefits, but because it was universally assigned, it accidentally became America's primary key. A primary key is a unique, non-repeating identifier used to distinguish specific individual records in a database. Behind every assigned number was a physical ledger entry stored in a sprawling warehouse. This was the NUMIDENT. The numerical identification system is the master chronological record of all Social Security numbers, manually updated by clerks filing paper cards for every birth, name change, and death. Manually updating millions of paper records required immense physical space and endless human labor. As the population grew, the volume of records outpaced the speed of the clerks, making a physical paper process mathematically unsustainable and destined for complete failure. To prevent collapse, the Social Security Administration computerized the NUMIDENT in 1961. The entire physical archive was migrated onto raw IBM mainframes, creating one of the earliest large-scale identity databases in the world. This early environment ran on 6-width schemas, which are database structures where every piece of data has an exact unchangeable character length. The system relied heavily on COBOL batch jobs. COBOL is an early programming language designed for business data processing that executes tasks in large scheduled groups rather than instantly. To get the physical paper records into the digital system, operators typed the data out, punching precise rectangular holes into paper cards. These holes translated human names and lifespans into a machine-readable language that was fed directly into the magnetic tape drives. Encoding human identity into strict, fixed-width rows eliminated the physical paper bottleneck. It allowed the government to automatically track and sort the legal status of citizens at an unprecedented national scale. By the 1980s, the administration began directly compiling death reports from states, funeral homes, and hospitals. Consolidating this data allowed them to release the very first public data extract of the deceased. This extract is the Death Master File, or DMF. The critical architectural distinction is that the DMF is not a standalone database. It is a smaller projection filtered down from the massive NUMIDENT master file to only include specific data points like dates of death and internal verification codes. Today, the NUMIDENT still relies on those legacy COBOL batch jobs running on mainframe architecture. To process claims and verify identities, these older nodes must somehow integrate with modern Oracle databases. Oracle databases are modern systems that store data in highly structured, easily queryable tables. Bridging this gap requires an ETL pipeline. ETL stands for Extract, Transform, and Load, which is a complex data engineering process that pulls 1960s mainframe records, reformats them into modern schemas, and securely loads them into contemporary verification systems. America's entire modern identity infrastructure does not run on a unified, state-of-the-art system. It relies entirely on a fragile, continuous bridge between half-century-old legacy code and modern data engineering. A death enters this pipeline through multiple disjointed channels. Funeral directors file reports, state governments send electronic records, and hospitals transmit notifications directly into the government's legacy enumeration systems. But the system is not instantaneous. There is a gray zone, a dangerous latency period of hours, days, or even weeks between a physical death occurring and the death master file officially updating. This specific latency window creates high-stakes vulnerabilities. During these undocumented days, benefits are mistakenly paid out, identities are stolen, and massive financial fraud can occur without triggering any digital alarms. The gap only closes during the system's nightly reconciliation cycles. This is when the legacy mainframes finally cross-check the incoming state reports, validate the state change, and officially push the update to the master ledger. In the architecture of digital identity, timing dictates security. The temporary delay of critical information creates the exact same operational vulnerabilities as the complete loss of that information. In 2011, investigators realized criminals were actively exploiting the public accessibility of the Death Master file. Because the extract was openly available to genealogists and researchers, fraudsters simply downloaded the exact social security numbers needed to file fake tax returns for the recently deceased. Congress forced an immediate architectural lockdown. Millions of state-reported deaths were scrubbed from the public file, resulting in the creation of the Limited Access DMF, or LAD-DMF, a highly restricted private version of the dataset. Accessing the LAD-DMF now requires navigating stringent operational rules. Institutions must obtain federal certification, undergo independent security audits, and prove strict compliance controls just to view the true, unredacted records. Providing open access to identity records enabled mass fraud, while completely restricting them would prevent banks from closing accounts. Securing a foundational national system without breaking the economy required splitting the ledger's truth into separate public and private layers. Even behind locked servers, the system faces immense data quality challenges. Because inputs come from 50 different states and thousands of funeral homes, inconsistent reporting constantly generates duplicate keys, century-old birth dates that remain active, and requires machine learning just to detect anomalies. Yet the broader economy is completely dependent on these inputs. This identity ecosystem includes massive institutions like banks, credit bureaus, and Medicare, which rely on the Death Master file to prevent fraud and manage the financial ends of human lives. To survive the scale of the population, the system has constantly adapted. It evolved from a vulnerable paper warehouse to a bare metal mainframe, and finally into a highly secured, modern digital infrastructure. The Death Master file dictates who is alive and who is deceased in the eyes of the state. It quietly operates in the background, continuously processing the end of life to forever define the digital boundaries of American existence.